You ever wonder how a spell checker just knows what you meant? Like you type kitten, but it suggests sitting. It feels like magic, right? Well, it's not. It's math. It's measuring the distance between words. And today, we're going to solve exactly how that works using a really clever technique called dynamic programming.
So let's just frame the puzzle right here. How would you actually measure the difference, the so-called distance, between two words like Saturday and Sunday? I mean, we can now tell they're pretty similar, but how do you put a number on it? How many steps would it really take to turn one into the other? That's the core question we're going to tackle. And this idea has a formal name. It's called edit distance. It's defined as the absolute minimum number of operations it takes to transform one string into another. We're not looking for just any path. We're looking for the shortest path. Our whole goal is to find that one single number. Now, to find this shortest path, we have to play by a very specific set of rules. We're only allowed to make 3 types of moves, okay? We can insert a character, we can remove a character, or we can replace one character with another. That's it. Every single change has to be one of these 3. Now, look, we could try to just guess our way there, right? Randomly swapping letters, deleting things, but that would be a complete mess, and we'd probably never find the best answer. So, no. Instead, we're going to be way more strategic. We are going to build a map, a grid, that will guide us step by step to the single most efficient path. And here it is. This is our map. It's just a simple grid. We're going to put one word, Sunday, across the top, and the other word, Saturday, down the side. Now, here's the real key. Every single cell in this grid is going to hold a tiny piece of the final answer. Before we dive into the deep end, we need to set up the edges of our map. So let's start with the absolute simplest cases you can imagine. What's the cost of turning a word into nothing, or turning nothing into a word?
Well, the answer is pretty obvious when you think about it. To turn ST into an empty string, you just need 3 deletions. To build SU from scratch, you need 3 insertions. So we can fill in that first row and column just by counting up from 0. And of course, the top left corner, transforming nothing into nothing, that costs 0.
And this is the most important idea to get. This is the whole point. We are not solving the big problem all at once. Nope. Instead, every single cell in this grid holds the answer to a much smaller, bite-sized version of the problem. Like, what's the edit distance between just saw and Sue? By solving all these little mini-puzzles first, we build our way up to the final solution. It's guaranteed to be the right one. Okay, our boundaries are all set. Let's fill in our first real cell. You see the one highlighted here? This box is going to hold the edit distance between the very first letter of each word, S and S. So how do we figure out what number goes in there?
It's actually super simple. We just look at the characters for this cell. In this case, it's an S from Saturday and an S from Sunday. Do they match? Yup, they do. And that makes our decision incredibly easy. So if the characters match, no work is needed, right? The cost for this step is 0. We don't have to do anything. So we just carry over the cost from the problem we just solved, which is always the value in the cell diagonally up and to the left. In this case, that value is 0. So our current cell also gets a 0. Easy.
Okay, but what happens when we get to a cell and the characters don't match? Like right here, we're comparing the A from Saturday with the U from Sunday. Clearly not a match. This is where the magic really happens.
This right here is the heart of the entire algorithm. When the letters don't match, we are forced to perform an operation. And remember our 3 legal moves? Well, they map perfectly to our grid. The cell to the left represents the cost if we decided to do an insert. The cell above represents the cost of a remove, and the diagonal cell represents the cost of a replace.
So since our whole goal is to find the minimum distance, the logic is really simple. We just look at the costs of those 3 possible moves, find the absolute smallest one, and then add 1 to it. That plus 1 is just the cost of the operation we have to perform right now because the characters didn't match. We're always choosing the cheapest path we've found so far and just adding our 1 new step.
Okay, let's actually do it. We're comparing A and U. They don't match. So we look at our 3 neighbors. Their values are 1, 1, and 0. What's the minimum of those 3? It's 0. So we take that 0, we add 1 for our current operation, and boom, the value for this cell is 1. We just keep repeating this simple, powerful logic, cell by cell, across the whole grid.
And by just applying that same simple rule over and over again, if the characters match, take the diagonal. If they don't, take the minimum of your 3 neighbors plus 1. We eventually fill out the entire map. Look at that.
Every single subproblem is now solved, and importantly, its answer is stored right there in the grid.
And now for the grand finale. After all that work filling in the table, where's our final answer? It's always waiting for us, right there, in the bottom right corner of our map. That number is the solution to our original big question. The minimum edit distance between Saturday and Sunday is 3.
So what about performance? Was all this map building worth it? Oh, yeah. If our two strings have lengths n and m, we just made a grid that's n by m in size. To fill it, we had to visit every single cell exactly once. That's it. This gives the algorithm a time and space complexity of O n times m. And it's so incredibly efficient because we never ever have to recalculate an answer we've already found.
So, let's just quickly recap the powerful strategy we just used. First, we took a big, scary problem and broke it down into a bunch of smaller, manageable subproblems. Second, we used a table to store all the answers so we'd never solve the same problem twice. And third, we built up from the simplest possible cases all the way to our final solution. This fundamental pattern, this is the very heart of dynamic programming.
So, okay, we've mapped the distance between words, but this exact same technique is unbelievably versatile. It's used in everything from aligning DNA sequences to, spell checkers. So the real question to leave you with is this. Now that you know how to do this, what other complex problems out there, things that seem totally overwhelming at first, could you break down and map out, one cell at a time?